In this program, we'll look at how to solve navigational problems using two different types of flight computers. First, we'll discuss the mechanical slide graphic, or CSG computer. Then we'll cover the TechStar, which is an electronic flight computer. Because this program is only an introduction, you should study the operator's manual for the computer you've selected in order to become thoroughly familiar with it. If you have a computer handy, you might want to work the problems as we're going through the program. We'll pause periodically to allow you to complete the problem. If you're only interested in the TechStar computer, you can forward the tape to that part of the program. The CSG computer has two sides, the wind side and the calculator side, which can be used to solve a variety of problems including time, speed, distance, fuel consumption, true airspeed, density, altitude, and conversions. There are three scales on this side of the computer. The outer, or A scale, can represent distance, fuel, speed, or other units, depending on the problem you're solving. The middle, or B scale, may represent similar items, as well as time in minutes. The inner, or C scale, is simply a conversion of time in minutes to time in hours and minutes. The outer scale is fixed, while the inner two scales are printed on a single rotating disc. The numbers on the computer can be assigned different values depending on the problem. For example, the 60 can have a value of 0.6, 6, 60, 600, and so forth. By mentally estimating the approximate answer, you can place the decimal point in the proper position. The graduations between the numbers, however, are not always equal. For example, between the 80 and 90, there are 10 divisions, with each division representing 1 unit. The third line right of 80 could be 8.3, 83, or even 830. Between the 21 and 22, there are only 5 divisions. Here, each line represents 2 units, so the third line right of 21 could be 21.6, 216, and so forth. Most of the calculations on the computer are ratios or fractions. For example, when determining time, speed, distance problems, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the third. The face of the computer shows you how to solve for the unknown value in these ratio problems. If your aircraft speed appears over the index, you will find distance on the A scale and time on the B and C scales. For example, assume you're planning to fly your airplane at 140 knots for a distance of 350 nautical miles. How long will your flight take? First, place the speed index under 14, which is 140 knots, when you mentally delete the 0. Then look under the 35, or the distance of 350 nautical miles, to find the time in minutes. In this case, it is 150 minutes. Notice that you have to add a 0 to the 15. 150 minutes can be quickly converted to 2 hours 30 minutes by referring to the C, or hour scale. You can also use the computer to find the distance flown in a given period of time. For instance, at a ground speed of 120 knots, how far will you travel in 2.5 hours? First, set the speed index under the ground speed of 120 knots. Then go to the C scale and locate 2.5 hours or 150 minutes on the B scale. Directly above this number on the distance scale is your answer, 300 nautical miles. You determine the ground speed of your aircraft in a similar manner. If you've traveled 349 miles in 2 hours and 15 minutes, what is your ground speed? First, locate the time for this flight. Since 2 hours and 15 minutes is not marked on the C scale, you should use the time in minutes, 135 on the B scale. For 349 miles, you'll have to estimate the distance from the line representing 345 and the one showing 350. Then you can read your ground speed directly above the speed index mark. In this case, it is 2.5 lines right of the 1.5. By placing the decimal in the correct position, you can determine the ground speed to be 155 knots. Fuel consumption problems are basically the same type of calculations, except that the index now points to the fuel rate, which in this case is gallons per hour. The outer scale shows the amount of fuel burned, while the inner scales still show time. Suppose in your flight planning you need to know how much fuel you will need if your destination is 3 hours away and your airplane burns 8 gallons of fuel per hour. Like the speed problem, set the index mark under the rate of 8 gallons per hour. Then find 3 hours on the inner scale, or 180 minutes on the middle scale. Read the fuel required, 24 gallons, directly above this time. Another type of fuel problem is to determine your endurance, or how much time you can stay aloft. Assume your airplane has 42 gallons of fuel on board, and it uses 11 gallons of fuel per hour. This time, set the index under 11, which is the rate per hour. Under the 42, read 229 minutes, or 3 hours 49 minutes on the inner scale. You can also use this side of the computer to determine true airspeed. However, to do this, you must know 3 things: calibrated airspeed, pressure altitude, and air temperature. While in the air, you can determine the temperature by referring to your outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned altitude from the winds and temperatures aloft forecast. If you're unsure of the pressure altitude and you're in an airplane, you can determine it by setting the altimeter to 29.92 and reading the indication. Make sure you reset the altimeter back to the current reported setting when you're finished. Calibrated airspeed can be found by referring to the pilot's operating handbook. Once you've determined all the necessary variables, use the window marked for true airspeed and density altitude and align the temperature in degrees Celsius over the pressure altitude. Then read the true airspeed on the A scale opposite the calibrated airspeed on the B scale. As a sample problem, suppose the pressure altitude is 5,000 feet, the temperature is 20 degrees Celsius, and your calibrated airspeed is 150 knots. Using the proper window, align +20 opposite the 5. Notice that the altitude scale is in thousands of feet and plus temperatures are to the left of 0. Next, find the calibrated airspeed of 150 knots on the B scale. Then read the true airspeed of 166 knots on the A scale. Density altitude can then be read directly from the center window. If the conditions remain the same as in the previous problem, the density altitude will be approximately 6,700 feet. The other window is used to compute true altitude. Instructions are listed near the window. The computer can also be used for conversions. For example, a temperature conversion scale is located at the bottom of the disk. For nautical statute mile conversions, 2 arrows at the top of the fixed scale give the proper relationship. These and many other conversions are covered in your owner's manual. The wind side of the computer is used to determine how the wind is affecting your airplane's ground track and speed. As you learned earlier, the moment an object becomes airborne, it is affected by the wind. If the object has no propulsion of its own, such as this balloon, it will float at the same speed and in the same direction as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, also will have drifted this same distance. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. The wind side of the computer helps you determine to what extent you'll have to fly into the wind. There are two parts to this side of the computer: a rotating azimuth and a sliding grid. Notice that the grid is printed on both sides. The high-speed side is used mainly for solving problems at jet speeds. There is also a statute and nautical mile scale, which can be used on sectional and whack charts. The low-speed side of the scale is used for aircraft flying at lower speeds. It contains concentric arcs, which represent speed, and straight lines radiating from a central point, which represent degrees right or left of the center line. The rotating azimuth is graduated into 360 degrees. The center of the azimuth is a frosted transparent material, which can be marked on with a pencil. Directly in the center is a round circle known as the grommet. At the top, on the fixed portion of the computer, is a true index, which is used as a reference for plotting wind and course direction. The center line printed on the grid can represent any direction by just rotating the azimuth so the desired degrees are aligned under the index. At the top of the grid are easy-to-follow instructions on how to find ground speed and true heading. To determine how wind affects your airplane, you will need to know true airspeed, wind direction and speed, and true course, which is your intended flight path as measured from the true North Pole. The method for determining true course will be explained in the next section. Suppose that you've determined your true course to be 310 degrees. The predicted wind at your altitude is forecast to be counting the number of degrees the wind dot is located from the center line. In this case, each line represents 2 degrees, so the wind correction angle is 6 degrees left. Since the correction is to the left, you must subtract 6 degrees from the true course to obtain your true heading of 304 degrees. To verify that these figures are correct, you can visualize that the grommet represents your airplane and it's heading toward the index mark. Since the wind is behind and to your left, ground speed should be higher than true airspeed, and the true heading should be left of the true course.